Welcome! In this video, we'll be tackling a classic problem in mathematics. Our goal is to find integer solutions for the equation x squared plus y squared equals 65. This means we're looking for whole number values for x and y that make this statement true. By the end of this lesson, you will be able to first, solve equations of the form x squared plus y squared equals z, where z is a constant. Second, you'll be able to quickly test integer values in such equations. This will allow you to find solutions efficiently. And third, you'll be able to identify patterns in integer solutions, which can help you solve similar problems in the future. So let's get started and find those pairs of integers that satisfy our equation. Let's begin by systematically searching for integer solutions for x. Remember, we're working with the equation x squared plus y squared equals 65. Since x and y are integers, x squared must also be an integer. It's a whole number squared. This means that x squared must be less than or equal to 65. If x squared were greater than 65, then y squared would have to be negative to make the equation work, which is impossible for a real number y, let alone an integer y. The largest integer whose square is less than or equal to 65 is 8, since 8 squared is 64. The next integer, 9 squared, is 81, which is too large. So, our possible integer values for x are limited to 0, 1, 2, 3, 4, 5, 6, 7, and 8. We'll test each of these. Now, let's test these possible values for x. This is a crucial step in finding our solutions. We'll go through each value for x from 0 to 8, calculate x squared, and then see if 65 minus x squared is a perfect square. This will give us our y value. First, if x is 0, x squared is 0, so y squared is 65 minus 0, which is 65. The square root of 65 is not an integer, so x equals 0 is not a solution. Next, if x is 1, x squared is 1, y squared is 65 minus 1, which is 64. The square root of 64 is 8, so if x is 1, y is plus or minus 8. This gives us our first two solutions, 1, 8, and 1 minus 8. If x is 2, x squared is 4, y squared is 65 minus 4, which is 61, not a perfect square. If x is 3, x squared is 9, y squared is 65 minus 9, which is 56, not a perfect square. Let's continue testing our remaining values for x to find any other solutions. We've already found solutions for x equals 1. Let's pick up where we left off. If x is 4, x squared is 16. Y squared is 65 minus 16, which is 49. The square root of 49 is 7. So, if x is 4, y is plus or minus 7. This gives us two more solutions, 4, 7, and 4 minus 7. If x is 5, x squared is 25. Y squared is 65 minus 25, which is 40. Not a perfect square. If x is 6, x squared is 36. Y squared is 65 minus 36, which is 29. Not a perfect square. If x is 7, x squared is 49. Y squared is 65 minus 49, which is 16. The square root of 16 is 4. So, if x is 7, y is plus or minus 4. Our solutions are 7, 4, and 7 minus 4. Finally, if x is 8, x squared is 64, y squared is 65 minus 64, which is 1. The square root of 1 is 1. So if x is 8, y is plus or minus 1. This gives us 8, 1, and 8 minus 1. So, we found all the solutions where x is a positive integer, or 0. Let's list them out. We have 1, 8, 1, minus 8, 4, 7, 4, minus 7, 7, 4, 7, minus 4, 8, 1, and 8, minus 1. But what about negative integers for x? A key property of squares is that squaring a positive number gives the same result as squaring its negative. For example, 1 squared is 1, and negative 1 squared is also 1. Similarly, 4 squared is 16, and negative 4 squared is also 16. This means that if xy is a solution, the next xy is also a solution. Therefore, for every solution with a positive x value, we can generate two more by changing the sign of x and y, and another 2 by changing the sign of x but not y. So we'll double the number of solutions we found, which was 8, to get 16. Let's put everything together and list all 16 integer solutions for our equation. Our full set of solutions includes the 8 we found for positive x and 8 more for negative x. First, we have our pairs involving 1 and 8. 1, 8, 1 minus 8, minus 1. 8 and 1 minus 8. Next, the pairs involving 4 and 7, 4, 7, 4 minus 7, 4, 7, and 4 minus 7. Then, the pairs involving 7 and 4, 7, minus 4, 7, minus 4, and 7, minus 4. And finally, the pairs involving 8 and 1, 8, 1, 8 minus 1, 8, 1, and minus 8 minus 1. You might have noticed a pattern. The solutions come in sets. If AB is a solution, so are A-B, AB, and A-B. Also, if the numbers are different, like 1 and 8, then 8, 1, and its variations are also solutions. This happens because the equation is symmetric in x and y. Let's quickly recap what we've accomplished and the strategies we used. Our main objective was to find all integer solutions for the equation x squared plus y squared equals 65. First, we used logical reasoning to find an upper bound for x. By testing x squared less than or equal to 65, we limited our search to integers from 0 to 8. This made the problem much more manageable. Second, we systematically tested each of these integers by plugging them into the equation. For each x, we found the corresponding value of y squared and checked if it was a perfect square. Third, we utilized the symmetry of the equation. Because x squared is the same as x squared, we were able to quickly generate all the negative and flipped versions of our initial solutions without having to do any extra calculations. By applying these 3 strategies, we confidently found all 16 integer solutions. You now have the skills to solve similar problems involving sums of squares. Keep practicing and you'll become very efficient at it. Thanks for watching.